I am not teaching, I am publicly learning. But hi and welcome to Learning for the Life in UK test part 153. Some Great British Inventions of the 20th Century, part 3, while doing the leg stretching. If you participate in my leg stretching, register your own risk. So the first stretch, we are bringing the leg in front, the heel onto the ground, and we're pulling the toes towards us. And from time to time, we're going to contract the quad muscles. Then releasing. So we're starting with contraction of quad muscles. We had the television by John Logie Bard, and then radar by Robert Watson Watt, and the first successful test was 1935, release for contraction. And then George Bank, he built the biggest radio telescope in the world in Cheshire, and contracting it. And then the Turing machine, it was a theoretical mathematical device made by Alan Turing, so it's named after him, the Turing machine after Alan Turing, release of contraction. And the theory of how the Turing machine worked, it was important for computer science and the modern day computer, and contracting it. So many computers, so how Alan Turing had built the Turing machine, and he had also other people working with him. That was a major step. It was very important for the development of computers, how computers are thinking in science. And then, now new, the Scottish physician and researcher John MacLeod, 1876-1935, was the co-discoverer of insulin used to treat diabetes, and release the contraction again. So John MacLeod, he was a co-discoverer, so someone else had took part in it, and for last time contracting of the quad muscles, of insulin, and insulin is used to treat diabetes. Diabetes disease, I don't know enough about it, and it's pretty well known all over. I don't really contribute to any knowledge if I spread my, not really, based knowledge. And the other leg in front, and we're putting the toes in, and we're contracting the quad muscles. So insulin by John MacLeod, co-discovered. It's used to treat diabetes. The structure of a DNA molecule was discovered in 1953 through work at British universities in London and Cambridge. And we're releasing contraction again. In Cambridge there was Isaac Newton and someone else. There was Clement Attlee. No, Clement Attlee was in Oxford. And we're contracting again. The structure of a DNA molecule was discovered in 1953 through work at British universities in London and Cambridge. So the DNA, we are releasing contraction, but it's in every cell of humans and also in animals and even plants. There is the DNA, and we're contracting again. And these are, I don't know exactly, but these are proteins, and there are millions of them, and they are set up in a way that this helps with humans or animals to become the animals. So in all these cells there's the DNA, and this DNA tells the cell, and we're relaxing it, how the human or the animal should be built up. So a dog has DNA in it, and the proteins are all like a code basically, and we're contracting again. And then the cells know, because the cells can't, it's not a brain, they can't think that the dog should have 4 legs and a tail and so on. And by humans, that the human should have 2 legs and 2 arms and fingers and so on. And we're using contraction for last time. So every animal, and also plants, have it in this DNA, and this DNA are millions of, basically it's like a code, and that tells the cell, we're contracting the last time, how it should be built up, how many fingers, how many legs, and also smaller things are in the DNA. Hair color, for example, or eye color, and so on. And we're going to the next exercise, the anchor chain stability test. We're having the leg actually outside and the toe points forward, and we're pressing the leg a bit into the ground. So in every single cell, also by trees, that the way these proteins, so it's just something, it's very, very little, in every single cell. There are millions of cells in the human body. In a tree there are cells in, and this DNA tells the tree it should become that type of tree or that type of tree. It just grows the way this codes tell it. That happens by itself. And then it becomes that type of tree. And by humans, there's in the cell written that it should have 2 legs. And in the cells of dogs, it's written that a dog should have 4 legs. And we're releasing the stretch a bit, but we keep the leg there. And this, that there are DNA molecules, that there is inside of cells millions of these proteins side by side. I don't know exactly. But it was discovered in 1953 through work at British universities in London and in Cambridge. And we're stretching again the leg a bit in the ground. This discovery contributed to many scientific advances, particularly in medicine and fighting crime. Francis Crick, 1916-2004, was one of those awarded a Nobel Prize for this discovery, was British. Francis Crick, one of those awarded the Nobel Prize for this discovery, was British. And over to the other side, toes are pointing forward, and we're pressing a bit into the ground with the leg. So that humans discovered that, so humanity discovered that in cells there are proteins, there's millions of them. And they are in all cells, I think, in years. They are in all human cells of a human, more or less the same, or at least they have, I don't know all exactly, but they are basically in all cells the same of humans. And that helped for advantages in medicine, because we now understand there is something inside of cells which tells cells how they should grow. There is something inside of every cell which tells that a dog should have 4 legs. Now the dog does not decide, I want to have 3 legs or 4 legs. Humans do not decide to have 2 foot and 2 hands. And the dog does not decide that it should have 4 legs. Maybe a dog could rather want 6. But it's just inside, and we're pressing again into the floor, inside of every dog to have 4 legs. And that we just discovered that there are proteins, there is something in lungs, there are millions of these things, and they are telling the cells itself how the cells should grow. That helped medicine, of course, because now we understood that is how a human body is built. So it works. Of course, we by far don't understand. Next exercise, the hydraulic cardiac. Leg to the outside, we're having a flexed foot, and we're bringing it up, and again back. Of course, we by the way don't really understand all about the DNA, but in 1953 we discovered that there was something, and that gave medicine an idea. And then there was done research to it in the last 70 years, and every day there's research done to it, and every day, from time to time, there are new discoveries, and we are at any given moment people working on finding better out what is we're working with this DNA in the cells, how we are building the human body. And also to fighting crime, because this DNA is in every single cell, of humans. Cells of humans are in the skin, for example, in every part of the human body, in the nails of humans, or in the hairs of humans. Now, and if there's a crime happening and someone commits a crime, they may be losing skin cells. So they are everywhere on the skin. And it can happen, and they are very, very, very small. So you don't see them when you lose them. Let's take the example of hairs, it's easier. And we'll draw the cutting on the other side. So sometimes people lose a hair. If you comb your hair or something like that, you'll find many hairs, or more hairs than usual. Where you see you can lose hairs. So sometimes you can find a hair somewhere. And it can happen with the person, when they commit a crime, that they lose a hair on the murder scene, on the crime scene. And now if the police comes, they're looking in every corner, very detailed, with flashlights, they're searching for everything, and maybe they're going to find a hair which the committing person has lost there. And now we can take that hair, they're looking under it under a microscope, or I don't know it, and we're looking very closely in that hair. And the hair also exists just as millions of cells. We're going very little in these cells, and when we're finding them, and when we're finding these proteins. And now we're looking, we have that type of protein, that type, and that type. And now we're listing them all side by side. We're finding I forgot all the names, but we're finding red protein and Debian, Epian, I'm just saying names. They have actually names which are pretty much like that. And we're having to find Debian, we're having to find Debian, Debian, and it repeats then after some time. Now to the next exercise, the car racer. Into 1990, and we're going with hands to the knee, which is behind us, and we're leaning in front with the shoulder to the other leg in front. And now we have said we have find Debian, 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 Debian. And if they have a few hundred of them in a row, they see, okay, it repeats now, this is the sequence. And every single of his DNA sequence is unique. Every human has a unique DNA sequence. So humans don't look the same. Every human looks different. So the plan on which humans are built is a little bit different. Almost all humans have in the plan to have 2 legs and 2 arms. But sometimes people are 10 centimeters higher, or their arm is a centimeter shorter. Or humans look a bit different. And this difference is in the DNA for large parts, at least. Not on the other side, and again the car racer. And humans are all related, all have 2 arms and 2 legs, or very much. But we look a little bit different. And also dogs. They look a little bit different. And so this DNA is not by every human the same. They are related. All humans get 2 eyes, a nose, a mouth, 2 arms, 2 legs, 10 fingers, 10 toes, and so on. But now they look a little bit different, so the plan is not exactly the same. If you look at another person, they are similar than the human in the anatomy, but there are little differences. You can distinguish them. You can look at a second person, they both don't look the same. So in the DNA, there are differences how the cells should be built up. That's why humans look different. So if we now find at the crime scene, into the 1990s stretch, just 1990 in the front, some DNA sequence, Debian, 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 500 of them, that is unique. There's not a single person, I'm going to it in a moment, in the world who has the same sequence. Every person looks differently from another one. And now if we have that order, Debian, 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 and so on, hundreds of them, we know that the person who was on the crime scene had that DNA. So we now know that at that crime scene there was someone who lost an hair and they had that DNA. Now, and if there was, now the pigeon test, I don't even know how to do it, if there was not a single other person, then we can say it's probably that person which lost that hair there, which had done that crime. We of course have to prove it better, but that hair was one there. And now we can take, if we have suspects, if we have 3 people, and we can now take who we are suspecting. They could be there at the time of the crime. And now we're taking a hair probe of them. We are taking a hair of them, and we're looking closely into all of the 3 hair examples which we got. And now we're writing down what proteins do we find in these hairs of these 3 suspects. The first suspect we find in TB, whatever. And the second suspect we find in Debian, Debian. And when we find another one who has Debian, Debian, and so on, and when we say, that is exactly the same DNA order which we found in that hair which we found on the crime scene. Now to the other side, first in the 1990 search, and now we can tell exactly that DNA, that hair is your hair. Of course we can look same hair color and so on, but after 10-20 hairs we are not able to distinguish them anymore. But with the DNA we can distinguish under millions of people basically who was there. So all of these suspects are making now a DNA example. We're looking in it, and if we're finding the same sequence of proteins in the DNA of them, we know you were there. And we don't just only find this in hairs, but also in every skin cell. You just need to touch something and your skin cells are there. Someone can take a probe there and can find that there is your DNA. Now we're a bit, it's not completely. So twins have the same DNA. That's why twins look the same. And I think I heard that it can happen, but I'm not sure if it's with fingerprints. So too, everyone has unique, because it's criminology, it's important. Now it's not. Twins have the same DNA. That's why they look the same. And I think it was DNA. Maybe it was fingerprints. That there's 1 in a million also has the same. So it's not 100% sure that it's just the person who was there. But it's very unique. It could be the DNA is actually unique, just not with twins. But I think it was DNA where 1 in 100,000 or so has the same DNA. But I don't, no. But it's just basically a little annotation, but it is not 100% sure. And the next thing, so the last exercise, the butterfly stage, even if you find the DNA of someone on a crime scene, that doesn't mean they have committed the crime there. But it is an important step in criminology. So, and the DNA, that there is a DNA molecule structure in cells was discovered in 1953 in London at Cambridge University. And a Nobel Peace Prize for that, a Nobel Prize, not a thanks. I thank you very much. Until next time.